Okay, we're going to do a little bit. I'm not doing all these exercises. I cannot. I'm going to do some, and I want to talk about number 6. There is a similar problem that is to do with closure. And so the first thing I'm going to do is, here is a method I hate. It works, but it's too slick. The set of limit points of A union B is the I don't want to give this method. I don't feel like it. Honestly, I don't feel like it. Let's use a good method. Okay? I hope I'm recording. Okay. And it's good to be sure. All right. Since A is a subset of A union B, we know at once that the set of limit points of A is included in the set of limit points of A union B. And in the same way, to save my aching fingers, we know that the set of limit points of B is included in the set of limit points of A union B. Therefore, what happened? Jumped out of the yellow. Therefore, this union of these two, both of them are subsets of the left side, and therefore any point that belongs either to the one or to the other has got to be in the left side. Okay? We shall now show that any number that fails to be in here must also fail to be in here. And it's because of this rather sneaky approach that I've chosen to do this exercise. Because you could have said the most logical and simple thing to say here is, I have just shown that every number in the right side has to belong to the left side. But then you can say, all right, now I'll show that every number in the left side has to belong to the right side. So how would you begin to do that? You would say, suppose that X is a limit point of A union B. It turns out that the proof is kind of unpleasant. You can push that home. It's actually nicer to show that any number that is not in the right side can't be here. The numbers here have to be in the right side. It's actually easier to write the proof. To prove, yes, we want to use a fancy long word with 5-syllable words. I'm good at 1-syllable words. Contrapositive, yeah, right? What I'm saying is, in order to show that every number in the left side has to be in the right side, I'll show that numbers not in the right side can't be in the left side. Same thing. Proving that every crow has feathers is the same as proving that anything without feathers must fail to be a crow. Okay? So, all right. So I'm announcing that this is the way I'm going to do it. You don't have to. If anybody wants to write something direct, Better send it to me. I'm telling you that it's a bit tricky to write. Okay. So we want to show that every number here must fail to be there. So how do you begin? Suppose that x is any number that does not belong to that. Isn't that how you'd start? To prove that every number that is not here eats chocolate. Suppose that x is a number that's not here. Now, you know what I know? I know that x is not a limit point of a, and I also know that x is not, I just spell not, a limit point of b. That's what I know, you see? All right. X is not a limit point of A. Talk to me.
It's not a limit point of A, so if it's going to be in the limit, the set of limit points of A union B, it's got to be a limit point of B.
No. I just wonder if you talk about X is not a limit point of A. What does it mean that X is not a limit? What happens? What has to happen when X is a limit point of a set? Yeah, let's spell it out. I want to actually, yeah, that was the method I hate. That's why I decided not to write. It's too slick. It's quicker. It's quicker and simpler than what I'm doing, but it's over slick. And you can say, ooh, who would have thought of writing? No. So I want to give a more earthy approach. So I'll stop myself just in time. What is the definition? X is a limit point of a set A means that for every delta greater than 0, the stick center X radius delta contains at least one member of A other than the given number whose name is Charlie or what, X. Right. Using the fact that X is not a limit point of A, we choose. Because we know, look here, X is not a limit point. It's not true that for every delta greater than 0, if it's not true that for every delta the then means there exists a delta for which the doesn't work. Right? It's not true that everybody in the room can speak French. What does that mean? There exists somebody in the room who can't speak French. Right? How would you use that information? You would choose somebody in the room who can't speak French. It might be valuable to know that somebody can't speak French. Then you can conduct a conversation without that person knowing what you are saying, or whatever it happens to be.
You know not to pick them to be
Yeah.
ambassador.
I have heard some very interesting stories of people who've engaged in certain conversations assuming that somebody else in a bus or a train is not going to understand. There's some interesting, cute, true stories, but I'm not going to tell them to you now. So anyway, using the fact that X is not a limit point of A, we choose a number. I'll call it delta 1. And I'll put a positive sign, greater than 0, right? Such that the stick center X with radius delta 1 intersected with A, thank you so much, slash singleton x must be empty. Do you understand? Now I'm going to say to you, actually, I think I can get away with murder. I can just, using the fact that x is not a limit point of b, we choose a number called delta. You can call it delta 3 if you like. There's no logical reason why you can't call it, you know, you can call it mincemeat if you like. Such that the interval center x with radius delta 2 intersected with what? B slash singleton x is empty. The next word in this proof, the next word, define delta to be the smaller, right? Smaller of the two numbers delta 1 and delta 2. We see that delta must be positive because it's one or other of two positive numbers must be positive. We also see that if you take the interval center x radius delta and intersect it with A union B and chuck out the point x, where'd that come from? You must get the empty set. You know why? Well, look, any number that belongs here, because it's in that interval, it's definitely in that one. Isn't that right? Mm-hmm. So there's no way it can be an A, right? But any number in this interval is definitely in that one, right? So there's no way it can be in B. And if you're not in A and you're also not in B, you're not in the union of the two. You see? There you are. So that is a very sort of earthy, direct, reinvent the wheel kind of approach. It is more convenient to write it this way than to try and say, let's assume that x is a limit point of A union B and try and prove that it's got to be a limit point of one of them. You'll be led, you know what, you'll be finished up, you'll write a proof by contradiction. This is probably, it's the same proof by contradiction in a sneaky way to avoid saying to obtain a contradiction. So anyway, number 7 is very simple. 10 I did, that's a very important exercise. 12 I've got to do. Not doing them all. I'm inviting people to send me stuff. Have a bash at it. Never try to answer an exercise until you have put yourself in a position of being able to rewrite to your own satisfaction that if you were standing before an audience giving a talk that they'd love you. Not a single hesitation. And by the way, when you are standing before an audience, you're speaking from the heart. If you ever have anything to say mathematically, don't work from notes. Quite honestly, the only thing that you should have in front of you when you are talking about mathematics to somebody is your coffee cup. Or to those who can't drink coffee, I suppose Diet Coke. Or classic Coke, I don't know. I mean, get these Coca-Cola fanatics. Are there any people here who line up every April to buy the true classic Coke that doesn't have corn syrup in it? I know, I meet people who do this. Comes out once a year. The ones with the yellow tops. You don't know what I'm talking about. I don't do this. I'm a coffee person. Anyway, but the original formula, that old formula that they make it once a year. Okay, so suppose that S is a set of numbers and that S is not empty. Excuse me, I can't read. What is this? L of S is not empty, and that delta is greater than 0. Prove that there must exist two numbers x and y unequal to one another whose distance apart is less than delta. Are you ready? We are given that L of S is non-empty. Yes? We are given that there do indeed exist limit points of the set. Yes? So what can I do with that information? Choose a what? Choose a chicken. Choose a what? I know that there exist limit. Choose a limit point. Should we give it a name? You want to call it X? I feel uncomfortable about the use of the letter X because we're going to try and prove the existence of two numbers and we're going to use X and Y for them. So let's use a different letter. Well, I'm prejudiced in favor of W because when I use too many T's, some of my students start writing capital T's because they can't make a nice little T. Their T's look like plus signs. I don't know. I think it's something to do with the elementary school teachers. The teachers do two things I don't. All the important people are here. So, okay. The other thing I don't like about what the teachers do is they teach from notes. You should teach from the heart. Carry in your coffee cup.
I thought you were going to say you didn't like tea because of like tea versus
Tea, not notes. Go to a concert. Does the soloist read from music?
occasionally.
Very seldom. Very good soloists play from the heart. Okay, so, all right, choose a limit point W of S, yes? Choose a limit point. Now I want to prove that something happens for every positive number delta. How do you prove that something happens for every positive number delta? Suppose that delta is greater than 0, yes? You could possibly leave that out and say delta greater than 0 was provided in the problem, I won't reintroduce it. That's gray area in this case. I'd be happy either way. I don't feel comfortable with the interval center x radius delta. That was my first thought. My first thought was to look at x minus delta, a nice piece of number line. That's not a nice piece. That's a nice piece. And then x, and then the piece of number line again, and then x plus delta. That was my first thought. And I know that in here, there have to be infinitely many different members of the set S. Isn't that right? And so, oh, goody. If there have to be infinitely many, then there have to be at least two. we could choose two different members of S in here, but one of them might be just near the left edge, and one might be just near the right edge, and how far are they apart? Almost as much as 2 delta, do you see? And I want their distance apart to be less than delta, so this is worthless.
Or what if you
Yeah,
choose X and then say
yeah.
X?
We use the fact that the interval here, not that one, but that one, must contain at least, well, infinitely many, infinitely many members of S. Don't we know that? To choose two members X and Y in this interval. In other words, the picture that I want is not this, but instead, I don't want delta here. What do I want? Delta over 2 there and there. They should be W's. You are absolutely correct. I use so many X's that I forgot that I'm not allowed to use an X now. Okay? And now, finish. Here's what you're going to write. Choose two different numbers, X and Y, unequal to one another, in here. And the distance between X and Y is the larger minus the smaller is going to be less than this minus this, which is delta. You understand? That's how you do it. Okay, neighborhoods of infinity. I asked you to go and read this. It's about 3 lines long. It's very short. Neighborhood of infinity. A set U of real numbers is called a neighborhood of infinity. Well, I'd like to say if all numbers close to infinity have to be in the set. How do you get close to infinity? You're not going to take around infinity a stick center infinity radius delta, are you? You can't do that anymore. How do you come close to infinity? You are close to infinity when you are big enough. Isn't that right? Look at the definition. A set U of real numbers is called a neighborhood of infinity if for some number W, there exists a real number W such that every number greater than W belongs to you. When is a set U called a neighborhood of infinity? When there exists a real number W. For some real number W, we have a guarantee that every number greater than W, all numbers here, every number greater than W must belong to you. And a neighborhood of minus infinity is similar. Now, I've already told you to go read it. Now, go read it. Okay? That's all I have to say about neighborhood of infinity. Take a look at this. It's very simple, quick. I don't intend to waste time on it. I want to get on to sequences. We are beginning a new topic. And I'm going to follow the famous textbook of a gentleman by the name of John Kelly, spelled Kelley, and introduce concepts here called frequently and eventually. And then I'm going to be talking to you about the idea of a limit of a sequence and a partial limit of a sequence. Eventually, I'm going to produce something for you by somebody else named Kelly, but that is her first name. And I was sitting with her in the Caribou Coffee just close to West Paces Ferry, battling to teach her this material, and I suddenly said, here is A Tale About Tales. And all of a sudden, she started understanding, and she finished this course with an A. So we're going to be doing these two things from two different Kellys, totally people who I don't even know whether John Kelly is still alive. If he is, he's probably about 150 years old. So anyway, even older than me. So I'm only 149. But okay. I want to tell you about these concepts called frequently and eventually. So here, the concepts. Frequently. Frequently and eventually. So what does it mean in plain ordinary English? You are frequently late for work. What does that mean? It doesn't mean that you're always late for work. It means that it keeps on happening, even though sometimes you're not late for work. Okay? That's what frequently means. Eventually means when something's eventually this happens, you are eventually dead. Right? It doesn't mean that, well, then you come alive, then you go dead again, right? Nobody's quite managed that, you see? So that's the difference, and now I'll give you the definition. I need coffee. A sequence XN is said. If you see the words say or said or write or written, you are looking at a definition. Okay, a sequence XN is said to be eventually. Eventually. If you want to know how I type this, down here is the text tag. And one of the fonts available, definitely in all my styles and in lots of others, is called Definition Bold. Okay? That's what I'm using. By the way, there's something called bold symbol. That's the font in which you make the set of real numbers and the set of complex numbers, the set of integers. Type in bold symbol. Okay. Eventually in a set S, a set to be eventually in a set S, if there exists a positive integer, big N, such that the condition x sub n, I really should have a little heading for eventually. Make the notes easier to read. If the condition x sub n belongs to S holds for every n greater than or equal to big N. A sequence is said to be eventually in a set if from some stage onwards and forever the sequence has gone in the set. You see, there's a much simpler concept. A sequence is in a set. And this is not set membership. Don't use a belongs to sign. A sequence is in a set when every one of the values of the sequence belongs to the set, you see. If xn belongs to S always, 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 then the sequence is forever in the set, you see. But eventually means something else. It means I don't know what happens for the first few values of n. But there comes a time when from now on, there's no more kidding around. You've had your time to sow your wild oats From now on, you will get in there and you will stay there forever. You see?
These are like moving sets?
No, it's a set. What's a moving set? S is a given set. S is the interval from 0 to 1. A sequence of numbers or a sequence of chickens, I don't care. A sequence is in that interval if there exists an integer big N such that from now on, for every n greater than or equal to big N, the value xn is in that interval.
How is that different from
How is it different from?
the lower bound?
Oh, I'm not thinking about bounds. I mean, you could have you could have a sequence. Look, you could have a chicken farm, and some of the chickens have green feathers. You have like a sequence of chickens. The sequence is eventually in the set of green feathered chickens if from some stage on the value is always a green feathered chicken. Nothing to do with bounds. See? Nothing at all. So that's the concept of eventually. Now let's look at frequently. Frequently. A sequence is said to be frequently in a set S if the set of integers, the set of values of n for which x sub n belongs to S is infinite. You following me? A sequence is said to be frequently in a set if there are infinitely many different values of n for which x sub n belongs to the set. Now, is there a difference between frequently and eventually? There'd better be, otherwise I wouldn't have used two different words. But how could it happen? I mean, you say if infinitely many values of n, the sequence is n, it means it's always n, isn't that right? No, yeah? You got an idea?
I have a question. What's the symbol that n is in the set for? I just can't see that well.
What?
Positive z.
Z plus.
Now, I've always used that for the set of positive
Oh, I just can't
integers.
see it.
Come down here. I won't bite, and I don't spit, mostly.
That's an idea for
Yeah. Yes.
the sequence of positive integers is frequently in the
Well, wait a minute. The set of positive integers, I didn't hear a sequence.
like
If you're going to give me a sequence, you've got to say, I define x sub n to b for every n.
call x and a sequence of positive integers. Like 1, 2, 3, and so on.
You want x sub n to be n. No, we can make things much simpler than this. I know that I'm stealing your thunder. Here's an example. Something much simpler. I'm going to define x sub n to be a sign flipper for each in a positive integer. Sign flipper. Now, do you notice that sequence xn is frequently in the interval 0, 1. There are infinitely many values of n for which xn belongs to that interval, even though there are a bunch of other values of n for which xn does not. You see? Do you see the distinction between frequently and eventually now? The example shows what the distinction is. See? I'm going to give you a condition. Let's go back to the definition of frequently. A sequence xn is frequently in a set S if and only if the set of integers, positive integers, n, for which x sub n belongs to S is unleaded, unbounded is almost there. You're right, actually, with unbounded, but I'm looking for something more clear. Unbounded above. It's always bounded below anyway, so you could argue unbounded is the same as unbounded above, but let's be clear. A set of positive integers is infinite if and only if it is unbounded above. Let's check this. Suppose you took a set with only 29 positive integers. One of them is biggest. That biggest one might be 1,000,000. You understand? When I say I've got a set of 29 positive integers, they might be 2, 4, 6, 8, 10, 12, up to 58 or something, you see? Or I might be a little more ambitious or imaginative, you see? But if you took finitely many positive integers, one of them has to be biggest. And that one would be an upper bound of the set. You understand? A set of positive integers that is infinite has to be unbounded above, and a set of positive integers that is finite has to be bounded above. You see, so an alternative way of saying this, a sequence is frequently in a set if and only if the set of values of n for which xn, what has happened here? What on earth? X sub n. I'm typing, right? In this is unbounded above. Same thing as infinite. See? Now I've got something to say to you. We assume that sequence xn is eventually in S. And I want to make a conclusion. Okay? Choose an integer big N such that x sub n belongs to S for every n greater than or equal to big N. Are you following me? We see that the set of integers n for which x sub n is in the complement of S is bounded above. Can you see that? I said, let's assume that sequence xn, I'm trying to get to my mouse. Let's assume that sequence xn is eventually in S. What does that mean? It means that
there exists a
that there exists an integer big N such that from now and forever after, the value xn must belong to S. Well, if there exists such a big N, how do you use the existence? You say, choose. Now look at the set of values of n for which xn is in the complement. This set is bounded above. Do you know why? I have in my pocket a known upper bound. What? Big N. You see? Because can any members of that set be bigger than big N? What do we know about big N? For every n greater than or equal to big N, what happens? Xn is here, right? So therefore, big N is an upper bound of that set, you see? And so, sequence Xn cannot be frequently in the complement of S. I said, suppose that sequence Xn is eventually in S.
We're not talking about specific members. We're talking about whole sequences.
I'm talking about a sequence. I've got a sequence. And I'm saying assume that the sequence is eventually in a given set called S. And now I'm saying choose a positive integer, call it Charlie or anything you like, such that from now and forever, from this stage, the value xn belongs to S. And then what can you say about the values of n for which xn is in the complement of S? None of these n values can be bigger than big N. Isn't that right? Therefore, that set is bounded above. Well, that makes the sequence unable to be frequently in the complement. If the sequence is frequently, what does it say? Eventually in S, it can't be frequently in the complement. Okay? All right. Now I'm going to say, let's put it this way. We assume that sequence xn is not frequently in the complement of S. You understand? What can I do with that information?
There's not an unlimited number of ones for which.
We are assuming, I'm trying to get, we are, let's see if I can get my fingers on the keys. We are assuming, what is going on here? We are assuming that the set of values of n for which x sub n is in complement of S is bounded above. Okay, let's go back. What does it mean for a sequence to be frequently in a set? What does it mean? The set of values of n for which xn is in the set is infinite. Or equivalently, a set of positive integers is infinite exactly when it is infinite when it's unbounded above. Okay? So I said to you, a sequence is frequently in a set if and only if the set of values of n for which xn is in the set is infinite. Equivalently, when the set of values of n for which xn is in the set is unbounded above, because a set of positive integers is infinite exactly when that set is unbounded above. Okay.
Is that supposed to be an if and only if statement?
Where?
The first frequently definition.
A definition is always if and only if.
Okay.
Every definition, when you say something is said to be, when it's the word said makes it's the definition. Yeah.
Why you put it there.
Every definition is an if and only if.
Included.
So now, I'm assuming that a sequence is not frequently in a set. What does that mean? It means that the set of values of n for which xn is in the set is bounded above. Right, well, help me use this information.
Choose an upper bound of that set.
Choose an upper bound. We just got to decide what to call it. Big N of the set of that set. Okay? Choose an upper bound of that set. Would you mind terribly if I don't call it Big N? I'd rather call it Charlie or something. Just because it's convenient. And define Big N to be equal to this number plus 1. I just want to be sure that Big N is actually above the upper bound that I chose. Now we can see that x sub n must belong to S for every n greater than or equal to big N. You see why I went one above? I said, let's make the assumption that the sequence is not frequently here. What does that mean? Not frequently. It means that the set of values of n for which xn is in that set is bounded above. Choose an upper bound. So no members of this set are above k. So I decided to just go a little bit higher to say no members of the set are here or higher, you see. For convenience. So I defined big N to be k plus 1. Now, for all n greater than or equal to big N, you know such n's are always strictly greater than k. You understand? Right, for all those n's, the xn is not allowed to be here. Where do you live if you don't live here? You're in S. And what is that? Going on over there. So xn is an S for all n greater than or equal to big N, and so sequence xn must be eventually in S. Look at these two statements. Assume that the sequence is eventually in S, and what was our conclusion? It's not frequently in the complement. Then I said, assume that sequence xn is not frequently in the complement, and guess what? If you're not frequently in the complement, then you've got to be eventually in the set. If you're eventually in the set, then you're not frequently in the complement. So let's sum up. I know that later in this notes document, I've got exactly these headings. I'll come to you in a second. I can't talk now. Sum up. Here it is. A sequence xn is eventually in a set S if and only if sequence xn is not frequently in the complement of S. You're eventually in S exactly when you're not frequently outside S. If you're frequently out, you're not eventually in. If you're eventually in, you're not frequently out. Okay? I think I'm ready. Talk to me.
So, at any point, are we going to talk about maybe a supremum or infimum of these?
That's the wrong question. I want to focus exactly on what we're saying. If there's something that wasn't clear. The plans for the future, I don't have room in my mind. Yeah.
Was the reason you chose n to be k plus 1 because the supremum could be the set?
I just wanted to make sure I get out. Yes. Yes, you're quite right. The reason why I was nervous about using the supremum is that it might belong, you see. So I went one up and said, now, I'm above an upper bound. I'm not in from now and forever. I'm not in. So this was just to guarantee that for all in, because you see my definition said for all in greater than or equal to big N. So I didn't want the big N to be a possible exception. And so I went one above just for safety, just in case the supremum belonged. You see, I said choose an upper bound. Okay? Well, by accident, I might have chosen the largest member. That's a damn nuisance, you see. So I said, listen, get away from there. Go one up. You see, from now and forever, you're not in. You see? That's really what it is. Okay? All right. So I've introduced these concepts frequently and eventually. Let's have a look at this. I've got some examples over here for you to look at. Please look at example 1. I'm also leading you into the text, and listen carefully to me, everybody. While preparing to talk to you today, I reworded some items in section 7.1 in the text. So there will be a new build of the text, a service pack that will say March probably 13. You are aware how to upgrade. You click in the table of contents, check for update, and you click and it just installs. And I want you please to make sure that you are absolutely up to date. Okay? All right, now look at this example. We are defining x sub n sometimes to be 1 and sometimes to be 0. If n is 1, 2, 3, 4, 5, 6, 7, 8 up to 20, the value xn is 1. And from then on, the value xn is always 0, right? This sequence is eventually in any set that contains the number 0. Is that reasonable? Take any set to which 0 belongs, this sequence will be eventually in that set. Okay? All right. Now, I thought I would take a slight variation on the sign flipper. This is sometimes equal to 2 and sometimes equal to 0. Isn't that right? It goes 0, 2, 0, 2, 0, 2, 0, 2, right? This sequence is frequently in singleton 0, not eventually. And it's frequently in singleton 2, right? It's eventually in the set containing 0 and 2, yes? And in fact, always in there. You understand? It's not eventually in singleton 0, but it's frequently there. Is that clear? Just thought I'd make this plain. And example 3, I want you to look at very carefully with me. We are defining x sub n to be 1 over n for every positive integer n. How do you feel about this sequence? X sub 1 is 1. I'm sorry, my hands won't appear in the video. X sub 2 is a half. We've come down a bit. X sub 3 is a third. X sub 4 is 1 over 4. X sub 29 is 1 over 29. X sub n for every n is 1 over n. In the language of Calc 1, you would say that this sequence tends to 0 as n tends to infinity. Can we say that today? I have no idea what it means. We haven't got a definition. Are we going that way? You betcha. The purpose of all this is to make the definition easier. Okay, right. We shall observe. Let's make a new line. We shall observe. This is my purpose. My objective is to prove that whenever epsilon, for a change, I didn't use a delta. You would prefer a delta? I've got to wean you off the delta and use some other Greek letters. Whenever epsilon, if you want to make this for a scientific notebook, my recommendation is do a Control G and then hit the E. It'll make, okay? So, all right. So, prove that whenever epsilon is greater than 0, the sequence is eventually in that set. I want to prove that for every epsilon greater than 0, the sequence is eventually in that interval. How do you prove that something happens for every positive number epsilon? Suppose that epsilon greater than 0. How do you prove for every? Say, suppose. Suppose, look, suppose that epsilon, you see why these words are here? Suppose that epsilon is greater than 0. Here's the interval. I'm saying choose any integer, big N, greater than 1 over epsilon. You know you can do that because the set of all integers is not bounded above, right? Right. Of course, this is an old thing. We've done this before. 1 over big N is less than epsilon. Isn't that right? For every n greater than or equal to big N, 1 over n will be not more than 1 over big N, and it'll also be less than epsilon. So I have trapped 1 over n into that interval for all n starting at big N and forever without any exceptions. The sequence is now eventually in that interval. You understand? I managed to get my hands on an integer called big N such that from now and forever, without any exception, the value 1 over n will be in that interval. How do you do it? Well, actually, it was quite easy. You choose an integer big N greater than 1 over epsilon. That makes 1 over big N what? Less than epsilon. Okay? And now, for every n from big N on and forever, for every n greater than or equal to big N, 1 over n is not more than 1 over big N, and that's already less than epsilon. Gotcha. You see? It's in there. Okay? Because they're all positive, so you don't have to worry about that. Then I've got some properties of eventually and frequently. You're going to be disappointed. I'm going to be repeating to you exactly what I've just done with you today. The first thing is, if a sequence is in a set, always, always, always in, then it's eventually in. You know why? Well, if it's in from n equals 1 onwards, then certainly you could just put big N equals 1. You understand? Number 2. If a sequence is eventually in a set, then it's frequently in the set. Is that clear? If it's eventually in, then it's always in from some stage on. Well, then the set of values of n for which xn is in, of course it's unbounded above because it contains all positive integers from some stage on. Is that?
Finite sequence.
Nothing to do with it. Oh, no. A sequence in this context is a function defined on the set of positive integers, or if you want to be a bit fancier, you start with any integer k and you go up from there. Okay. That's the sequence. Okay. So when a sequence is eventually in a set, it is frequently there. But do you think that every sequence that is frequently in a set has to be eventually? No. I've given you examples. And this is repeating what I've already given you. That it just comes back. I'm just making you rethink these things over and over again. And here I drew a nice picture. I should actually have put this picture up here as well. Let's see. Let's put it here as well. Because I've got a sequence that was eventually in a set, so it can't be frequently in the complement. I thought it might be nice to have a picture. And when the sequence is not frequently here, it's got to be eventually here, right? And it just appears back here. You understand? I'm just repeating myself deliberately. And yeah.
So the intersection of this empty set?
The intersection of this and this, well, the intersection of any set with its complement is always empty. Yeah. And of course, I'm showing it two-dimensionally because it's nicer for the picture. But I'm looking at a set of numbers and then the complement of that set in the number line, the set of numbers that don't belong. But one day, of course, it'll be in 2 dimensions or more exciting spaces. Okay? All right. I think I'm ready to give you the definition of a limit of a sequence. And we're not going to go very far with the definition. I've got enough time to give you the definition. We're not going to go very far with the definition. If you consider the beginning of Calc 1, a typical Calc 1 course begins with a half-hearted attempt to tell you what is meant by the limit of a function. I'm not sure how many of you got some kind of definition chucked at you, and you looked at it with absolute horror if you got it. And then you discovered about 2 lectures later that it wasn't going to play any role in the course, and that it was basically an April Fool's joke given to you, and it wasn't even April. You might be interested to know that I never, ever give a formal definition of a limit of a function when teaching Calc 1. Never. I know how hard it is to come to that. You first got to go through all the stuff I've been teaching you with greater or lesser success in chapter 5 and chapter 6, all the stuff with the neighborhoods and everything, and making sure you understand all the supposers and the choosers and everything and the language. And to do that with the little darlings who come into Calc 1 and they haven't even had the basis. And one of the hardest things is they haven't had a course in geometry, because there hasn't existed a course in geometry in American high schools for the last at least 25 years. There's a course called geometry. There is no geometry in it. It's a fake. Occasionally get a student who comes from Kenya or somewhere and he knows some geometry. So, okay. So, and that's where you learn the language, you see. All the supposers and the choosers, that's where you should learn it. Trouble is, the people teaching it haven't learnt it themselves. So anyway, I think I'm going to give you a definition of a limit, but this is of a sequence. I'm not going to give you a definition of a limit of a function defined on an interval or a function defined on something else. That's the way it starts in Calc 1. That's harder. We're not ready for that. We're going to do sequence. Sequence is easier. And the funny thing is that limit of a sequence is something that you learn in Calc 2, isn't it? So the Calc 2 one is easier and the Calc 1 topic is harder.
And supposedly Calc 2 is the hardest?
Well, yeah. Okay, here we go. I want to give you the definition and then we'll stop. A sequence. I think I'd rather word it this way. Suppose that sequence xn is a sequence of numbers, of course, and that x is a real number. Okay? We say, and you see the word say, what's coming? Definition. We say that x is here's the new word. Finally. Finally you're getting a limit. We say that x is a limit of sequence xn. And please note my use of the indefinite article here. In Calc 1, they usually talk about a number being, and I quote, the limit. Am I not right? Or why didn't I use the definite article the? We're going to need a theorem at some stage to say if there's a limit, there can't be more than one. Then I'll say, aha, if there's a limit, then there is only one. Now we can talk about the limit. We're being more careful. And don't expect to see any notation LIM from me today. That would give it a name. You can't give something a name unless you know that there's only one. Okay, here we go. We say that x is a limit of sequence xn if for every neighborhood u of x, the sequence xn is eventually in U. There is the definition of a limit. What makes a number x a limit of a sequence? That for every neighborhood U of x, no matter what, every neighborhood U of x, the sequence is eventually in U. There comes a time when it gets into U and stays there forever. That is the definition of a limit of a sequence, and it is this that we'll start studying next week. There are things called limits and partial limits. That's enough for today. And let me do something that I don't think I did efficiently on Monday. I'm suspicious that the lecture notes document from the CD on Monday might not be healthy, but Monday's lecture notes document will be healthy in today's disk, and it's fine in the website. But anyway, and today's should be fine. Did have how I stopped recording. Oh, what have I done? I'm trying to get this